Okay, in this video I'm going to be talking about thin film interference and working through how we can quantifiably predict what kind of what wavelengths we'll be seeing what kind of interference for. So the idea with thin film interference is that when light hits a barrier between two mediums, so if we were, say, for example, to look at air and water, this might be like the top of a lake or something. If the light basically can do three different things. It can be reflected, it can be transmitted, or it could be absorbed. When this happens, almost all the time, some of the light will be reflected and some of the light will be transmitted. What's interesting then, if we consider a thin film, where we have multiple barriers, one right after the other, maybe something like a soap bubble that's sitting out in the air, some of the light will be reflected off of the first surface, and some of the light will penetrate into the soap and be reflected off of the secondary surface. What this does is it creates a situation where one part of the light has a path length the other part of the light doesn't have. And so there's a difference in path length, and when we have two sources of a wave with a fixed path length difference between them, we can always get some sort of interference, be it constructive or destructive interference. I've drawn it like this to illustrate, but really if we wanted to consider this situation and we wanted to see the light that was interfering with itself, we'd really want to consider light that was going straight in and being reflected, and light that was going straight in and being reflected off of the second surface, where those two pieces of light are coming out at the exact same location. I drew it this way so you could clearly see the difference between the two pieces of light, but really all of these pieces of light should be right on top of each other. It's just a little confusing to look at it that way. For the purposes of this discussion, I'll be calling this piece of light, light 1, and this piece of light, light 2. And so when I consider their path lengths, L1 and L2, I'm talking about 1 and 2, respectively. So, again, this time in the film creates a path length difference, and that path length difference can be fixed in such a way that as a result the two pieces of light coming back together can add constructively or destructively. Now let's look at how we can quantify this, or what factors will affect the actual relationship between those L2 and L1. How can we figure out what kind of interference we're going to get? We have two main factors that are going to contribute here. The first one is the thickness of the film. So again, if I have my situation, I'll have air, soap, and air again. This film will have some thickness, and we'll use a T to represent that thickness. So when light 1 reflects off of the barrier, it will not go into the film, and so we don't consider the thickness of the film at all in its path length. But light 2, which is transmitted from the first barrier and reflects off the second barrier, goes through the film, and if we look at it, it goes through the film twice, and so it gets a path length associated with twice the thickness of the film. So whenever we have L2, we always add 2t to its path length, where L1 doesn't get anything for this consideration because it never went into the film. Secondly, we also consider the type of reflection. There's two main types of reflections that we need to consider here: fixed end reflections and free end reflections. I've done a separate video on what a fixed end reflection is and what a free end reflection is, but what's important about it is if the end of a rope or something tied to a wall is fixed, then when we put a pulse in, the reflected pulse will be inverted. From light's perspective, this occurs when the second refractive index is higher than the first refractive index. What that leads to is a path length change of half a wavelength. So if we want to consider a wave, and if this, we'll consider this our initial, with this starting point right here, when it reflects, if it's going to be inverted, it's like it's starting from this point here. That, if this is an entire wavelength, is like it shifted or like it traveled half of its wavelength. And so when we want to consider a fixed end reflection, or we want to cause the pulse to appear inverted, the way we can do that is we can change the path length by half of a wavelength. So when we look at this particular situation that I've created here with air, soap, and air, then on this surface of reflection, this would be N1 and this would be N2. So here N1 is 1 and N2 is 1.33. N2 is greater than N1, and as a result we're dealing with this fixed end reflection. And the way we handle that for path length 1 is we add in half a wavelength, and that is the path length associated with the inversion of that pulse. The other option is a free end reflection. A free end reflection results in the pulse not being inverted, and this occurs when the secondary medium for the surface of reflection has a lower refractive index than the first medium. In this situation, if we look at light pulse 2 or whatever, the one that goes into the film, then we're looking at this barrier between soap and air where it's reflecting on, we can see that N1 is 1.33 and N2 is 1, looking at this surface here, and so here N2 is less than N1, and so this is an example of a free end reflection. As a result, when I'm considering the path length, the reflected wave is not inverted, and as a result, there is no path length associated with an inversion. We just leave it alone, or we put a 0 in. Then we can create a predicted path length difference based on whether or not, or based on our specific situation here. So this one doesn't go in, this one does go in, and the resulting difference in travel for the light can be represented by 2t minus half a wavelength. Using that, we can predict whether we're going to get constructive interference or destructive interference. So for our specific situation, if 2t minus lambda over 2 works out to n minus 1 lambdas, then we would get a bright or constructive, or if you want to think of it as antinodal reflection. And in our situation, if 2t minus lambda on 2 would work out to n minus 1/2 lambda, then we would get very little reflection. And this makes sense, or depending on what we're doing with this film, if we're creating it ourselves, we might want the reflection to be very high or very low. For example, if we want to put a coating on a mirror that's going to help it reflect more light so that it's a more efficient mirror, we would try to make it a constructive interference situation. Or if we wanted to put a coating on some glass so we got very little reflection off the glass, maybe, for example, like on a pair of glasses that we would wear for like our vision, so that we don't get a lot of reflection so we can see the person's face behind the glasses, we would use a destructive interference situation with very little reflection, or what we would call an anti-reflection coating. There's one other small thing to remember when doing these equations, and that is specifically that the interference that we're going to be observing is going to be happening inside the film, not out in free space. And we have an issue with light or any wave, that its wavelength, remember the frequency of the light is constant when it moves from one medium to another, but its wavelength changes to allow it to change speeds. So here, the wavelength in the film will not, where the interference is actually occurring, will not be the same as the wavelength in free space. So we have to be careful and make sure we're accounting for that by using the wavelength in the film in these equations and not the wavelength in free space. Okay, having seen all that, I'm sure you want to see an example where I actually have, a real world situation. So I'm going to do that in a subsequent video, but that is how you come up with or predict the relationship of interference for a thin film.